Take a seat. We begin the session. This is a session entitled Curiosity on Mars. I recall that this session is split in two parts. The second part will be on Wednesday morning in this room. I also recall speakers that they have 12 minutes to talk in order to have several questions. And I'm glad to introduce you to John Grotzinger, our project scientist on Curiosity. Thanks a lot for being here, John. And John will give a review of what was going on in these last months with the rover Curiosity.
Great. Thanks very much, Nicholas. I'm here on behalf of all the principal investigators for the mission. They're named below here, and they all have their science teams, plus the participating scientists. There are over 400 of us, so I just want to thank everybody who's in the room here that works on the mission for all your hard work. We are just into solar conjunction, so everybody's just taking a breath here for a moment to think about maybe writing up some papers now. Okay, so again, just the background about Gale Crater. One of the things that was important to us was that there's the crater rim dissected with what are clearly alluvial features that were coming down towards the landing ellipse. Here's where we landed. The colors in the map here code to thermal inertia. So we were very attracted to this material as something to explore. We didn't know what it was going to be, but it was important because geologically it mapped out in front of the alluvial fan, and so there was a hope maybe that there might be a lake involved there at some point. But when the rover landed here, even though our primary objective was in this direction, we chose to go the 500 meters out of the way to go inspect the high thermal inertia terrain. As we drove along, we do what all rovers do. You go along, you stop occasionally, recharge, make measurements, and then keep going. Again, we were attracted to this rock, which was the higher thermal inertia unit, lighter toned. There was a third kind of rock down here that has a higher crater density preservation. And then there were these hummocky terrains that we worked across. So what I'm going to do is I'm just going to go very quickly what we did as we went across here. You'll hear more about that later. And then I'll talk about our drilling activity down here in Yellowknife Bay. Conglomerates. Along the way, we found pebble conglomerates, ancient alluvial gravels. I won't say much more about this other than they gave us confidence to just sort of go with the flow. And we used topography as a guide and the drive towards thermal inertia to keep us moving in that direction. As we went along, we found rocks that hadn't been seen before on Mars. These are things that the team thinks are pretty good examples of porphyries. And probably I'll guess that Sylvestre will tell you more about that in the ChemCam talk. But right off the bat, the ChemCam instrument began to get very high silica values, hitting some of these things that were probably phenocrysts of feldspar, and I think there's a pretty strong case to make there. As we went along further, we eventually found a rock that we did a coordinated experiment with to compare. These lines represent ChemCam shot points. The purple circles represent the cross-sectional area of the APXS instrument. We were trying to get a sense for what each was measuring. ChemCam is always tending to measure minerals, whereas APXS is integrating over a big area and tending to do chemistry, bulk rock composition. And what we got out of this was a rock that was very high in its alkaline content. There's a story behind that Ed Stolper is writing up petrologically. Again, these rocks are nepheline normative, and they're probably coming from significant depth of partial melting and the presence of a higher volatile content. So that was pretty exciting as well. We drove along, eventually had to find a place where we needed to clean out our sieve, but at the same time, the science team was really excited about being able to use Chemin and SAM on a material that had been measured many times on other rover missions, a typical Mars soil, so to speak, really a windblown deposit here. So we dug into that, scooped it up, and these are some of the important things that we saw up here. Basically, it looks global to APXS, looks like every other soil that we've ever seen. The interesting thing is we saw unaltered basaltic mineralogy. Probably Dave Vanneman will cover this. Interestingly, there were 30% amorphous materials in there, abundant volatiles, and we were able to measure the D to H on the water that was in there, and it looked like the modern atmosphere. Okay, coming back to the geology a little bit, so we landed down here, and we wanted to go to this triple junction where this light tone fractured unit, this high thermal inertia rock came together with these other ones, called that area Glenelg, and basically we drove down into the light tone fractured material. The important thing is to recognize geologically this is out in front of this fan. So when we moved the ellipse, we did it with a purpose. We wanted to get closer to Mount Sharp, but we also wanted to get closer to this stuff. We were really more interested in this than that. Okay, so this is what it looks like. You look up the topography, you see the dissected crater rim, probably with ancient rivers flowing out of there, and bringing materials into place here that form these strata, which are this light tone fractured terrain. And this would have been several kilometers drive. However, by going to the right, we got there in about half a kilometer or so. And then this is what we call the hummocky terrain. Sorry, this material here is the hummocky terrain. And what we wanted to do was to get up to the border where we crossed into this higher thermal inertia light tone material. So when we went then to basically driving to the east, this is what it looks like at the boundary between the hummocky terrain, which is a bunch of loose materials, and the light tone fractured unit, which is a solid bedrock, kind of looks like Moab, Utah. And as soon as you get beyond these outcrops, we drove the rover around here, the world changed for us in a really substantial way. And the most unexpected kind of result that the instrument wasn't built for, Javier Martin Torres will talk later about the REMS data, but something very important for us was that you could see the day-to-day diurnal temperature variations. And basically, when we drove across the boundary that we map based on the Odyssey data that takes us across this boundary where you go from lower thermal inertia to higher thermal inertia, when we drove from 120 to 121, we crossed that boundary, and you can see the temperatures thereafter are buffered. So that is the definition then of the high thermal inertia. So that was pretty cool to see then the atmospheric instruments being recorded, what the geology was predicting from orbit. Okay, the next thing that happened after we drove past it was the ChemCam instrument then looked down, and here's an RMI image that shows some light tone materials crisscrossing. Long story made short, those are fractures that are filled with a light material that we now know to be calcium sulfate. And at the time, ChemCam nailed this. This is what this instrument was built to do, was to give us remote sensing composition to about even really fine features. So this is not something that you would have necessarily have seen with an imaging spectrometer, but with the laser, you were able to nail these little tiny hairline fractures and show right away that those were sulfates there. And now the pulse of the team started to go up here, getting more excited about the presence of water. So then we drove down into Yellowknife Bay, and here's the regional, this is a 360 mass cam mosaic up here. You can see the rise of Mount Sharp way in the background. That rock nest soil locality was back up here. Drove around the corner, saw 120, took us into the high thermal inertia. Everything you see is high thermal inertia out here in the front. And this ledge that weathers back is a wave of erosion that is cutting the rock back from a sandstone, so blown up in the box here. This is all sandstone up here, fluvial sandstone, and what you have down here is a more recessive mudstone interval that's weathering away. This feature we call the snake looks like some type of a sedimentary intrusion. Probably compaction is going on here as you bury these layers, and the more ductile, liquefied sands are being injected up into the mudstone. Where we drilled is just off to the right. It's over here. We drove around for a while, found the best place, and decided to drill right there. This is a schematic stratigraphy of what we saw. Notice the scale here on the left. So we have this mudstone that we can prove it's very fine grain with the Moly instrument, crisscrossed by fractures filled with sulfates that not only cross that unit, but also cross the overlying sandstones. Here's this snake feature that transects the bedding plane as well. We've got concretions localized at particular intervals. And then we have a generation of fractures we don't really understand yet. They are raised relief. They stand up. They weather resistantly rather than recessively. And we're just getting information now on what the composition of these is. And again, ChemCam is very important because these are narrow features, and that laser beam really does a nice job of getting us in for the details. Okay, this is basically our canonical rock of the sheepbed mudstone. The matrix is very fine-grained. It's crisscrossed by these light-toned fracture fills that you see here, and it's laced with something that seems to be becoming more and more common on Mars. Rounded balls, long story made short, all of the evidence points to geologically towards these being concretion rather than impact lapilli or something, maybe volcanic lapilli. They have the density distribution that looks like concretions. Okay, now if you take an image, here's an area where the outcrop's been a little bit cleaner. You see the fractures going through, and sometimes there are circular voids that are also been filled in. We originally thought these were nodules. They're not. They seem to be voids that maybe some type of a bubble or something that got filled in there. Whatever they are, then when you look at them with MassCam, there's some work that Melissa Rice and Jim Bell have done with the near-infrared part of the spectrum between 900 and 1,000 micrometers. You get an absorption feature that, again, suggests these are hydrated calcium sulfate. So the ChemCam saw it first, gave us a sense there was something there. Now with MassCam, we can map these things all over the place. But they're a later feature. They're diagenetic, but they're a later phase of diagenesis. Okay, so then we got down with the arm and we got the brush out, and what we saw there was that we could clear the dust off the outcrop, and we've got our fractures, our hairline fractures that connect up between these more circular features, and when they are connected by the fractures, they fill with sulfate. When they are left behind and unfilled, they represent a void. And then we see features in positive relief that are also resistant. Notice how when the brush is grinding, it streamlines around these features, suggesting that whatever they are mineralogically, they're harder. And we think this is maybe a source of the iron that we see. You'll see the Chemin results in a minute. So we're going to do some more experiments to figure out what these features may be. Okay, but after we brush it then, we use the APXS to analyze it before and after the brush, and here are the results there. These are basically the highlights for a number of APXS analyses, and for the Wernicke target, the one I just showed you, basically the bottom line is when you brush these rocks, brushed are the red lines, the sulfur concentration goes down. And that was a big surprise to us because it's down so low. This is all compared and normalized relative to our average soil that we had back in the scooping area. So there's less sulfur in the rock than there is in the dust. And normally we're used to having the sulfur in the dust. Now the chlorine stays up, is a little bit higher, but this came as a big surprise. We're wondering what that cementing material is with these sulfate veins lacing through the rocks. They're certainly not cementing it. So we see a rock that's actually very low in salt content for a sedimentary rock. Okay, so then we drilled it, and you might have heard from the media proceedings that we were talking about red Mars versus gray Mars. Going into this, we knew from the APXS measurement, we knew from the ChemCam data that we had a relatively normal amount of iron in these rocks, and when we drilled into it, it was grayish green rather than red, which suggested to us in a qualitative way that maybe the iron was present, but in a more reduced state than hematite, which is what we had gotten used to with MER. This image shows our test hole, the final drill hole, and then after we're done analyzing it in Chemin for about 20 hours of integration time, plus 4 splits sent to the SAM instrument for evolved gas analysis, we then dumped it back onto the outcrop. So this is the part that moved through the 150 micron sieve. This is the part that didn't make it through. And then what we did, the last thing we did before conjunction was get the arm out and then lay in a raster of APXS spots over these different places. And during conjunction, we'll walk through this data and see what we've got there. Okay, again, sort of an iconic image for the mission. Here's our scoop filled in with the process sample. This is the stuff that made it through the 150 micron sieve. But again, this white balanced image, what it shows is this grayish, slightly greenish color, but with a little bit of residual contamination here left over from rock nest. So we weren't able to get the sieve and the scoop completely clean. So this is red Mars, this is modern Mars, this is ancient Mars that you see there. Okay, so then Dave Vanneman will go into this in more detail, but this was really exciting for us, was to get the Chemin results. This is this two-dimensional X-ray pattern that comes from the procedure that's used. And a lot of the reflections that you see here are basically coming off of the basaltic composition minerals, but the one that really captured our attention was this one down here, where we see the phyllosilicates that were first discovered by the Omega instrument and then seen all over the planet in key places, and again by CRISM. Here we were in a place where these were not observed before we landed. I think there would have been a lot of debate about whether or not there was anything worth where we actually drilled going to other than the high thermal inertia. But it just goes to show that this rock has about 20 to 30% phyllosilicate, so that's very important for us. Dave will go into this in more detail, but notice the comparisons here. The primary igneous minerals that you saw in Rocknest are way down in the rock, and we believe that's the effect of water causing their alteration. What goes up to replace them are these smectites that you'd see down here, 20 to 30%. The other mineral I want to key in on is magnetite, because we think that's where the iron may be. It could be authigenic. We're not really sure how these minerals have formed yet. The team is going to be discussing it, as you can imagine. So we'd like some time to work through it before we come up with our interpretations. But the fact that this is up so high and it's associated with a mudstone gives us some sense that it's out of hydraulic equilibrium. You don't have magnetite normally sorting out with a clay-sized material. So possibly this is some diagenesis, but going on at a lower redox state than what we're used to on Mars. The SAM data, also very interesting. Notice the temperature, basically, whoops, sorry. Temperature going up here. My laser pointer now wants to change the slide. Anyway, temperature going from left to right. What you see is the water coming off that's probably adsorbed from the atmosphere. It comes up again later on the right there at the temperatures that are consistent with the presence of clays, and we collect that water and look at it with the TLS, and we're going to get isotope ratios on hydrogen, deuterium, and oxygen isotopes, and probably we're going to get some of these sulfur isotopes here as well. But the important point I wanted to make here is that not only are we releasing sulfate, we're also releasing hydrogen sulfide. And so that tells us that we have mineral components in here, or at least their amorphous equivalents, with a variety of redox states. And that's important for the point of habitability. Just to close here now, we have two rocks, one from Meridiani, a decade earlier rover mission, one from Gale. At first pass, they kind of look the same, and the point is the story you have to scratch beneath the surface. This one is about the hematite that was produced. This one is about the magnetite and the clays that were produced. And it's also about the sulfate veins that are not iron sulfate, they're not magnesium sulfate, they're calcium sulfate. So basically, in conclusion, what we have here is something that we think is a habitable environment as defined by our level 1 requirements using all of the payload elements. We see a relatively neutral pH given by the presence of clays and the absence of iron sulfate. We see relatively low salinity given by the low total salt abundances and the absence of magnesium sulfates. And we see the presence of variable redox states in the mineralogy and the other compounds that are there by residual primary igneous minerals, the presence of magnetite, and also sulfate and sulfide. So we have a couple of different components here. Had there ever been a biosphere, we have components here that could have been used as terminal electron acceptors for lithoautotrophy, simple metabolisms. And then we also have carbon, measured and determined by SAM. And remember, we don't need to have organic carbon in order to have a habitable environment, because lithoautotrophs are feeding on the rocks using carbon dioxide. They don't need to have organics there before. And then the last one here, we are going here someday. We don't know when. That was the primary objective, but in the meantime, the secondary sort of plan turned out to be the primary plan. And thank you for listening.
Thank you, John. We'll try to stay on the track. So one quick question, if we have one. So maybe we'll move on. Thank you, John. Thanks. So next speaker will be David Vanneman, and he will present us data recovered by Chemin during the Mars Science Laboratory. Sorry. investigation.
Thank you, Nicolas. I'm going to talk about the first ChemCam results on Mars Science Laboratory. I'm part of a very large team. I didn't list all of the names, but everyone's help on this has been incredibly good, and it's much appreciated. The pictures here show the evolution of the Chemin instrument from a concept into the first prototype in 1991, up through a field portable version, and eventually to a marketable version of Chemin. This is actually a family of instruments now. This is marketed by the company In Situ. And finally, Chemin goes to Mars, 2012. The basis of the Chemin operation is in this CCD. Our detector is somewhat unique. It's an energy-sensitive CCD, so we can bin incoming X-ray photons by energy. So we sort out the cobalt, and again, well, here we're using a cobalt tube, not a copper tube. So some of the diffraction patterns you see might look a little bit odd. This is cobalt diffraction if you're used to copper. We're able to sort out those elements that are fluoresced and concentrate on the cobalt for a diffraction signal. And we also get XRF information of a sort from these fluoresced elements. But you'll notice that our efficiency tails off considerably about silicon and lower. So this doesn't give us full chemical composition. It is a crutch, though, that can help us sometimes in mineral identification. Our tube is a 28 kV, 1.5 amp filament current, very small, very effective. And it generally takes us about 10 to 20 hours, and usually 20 hours, to get a good diffraction pattern. So this is spread over several nights. Now, Chemin landed about 100 years after the discovery of diffraction by von Laue in 1912, very close to that. And here's a picture of some Laue spots. Laue, of course, used a single crystal method. With time and evolution of diffraction methods, it was realized that for complex multi-mineral samples, moving the grains in the beam will give you a much better and tractable pattern, and you get these Debye rings. And this is an actual image of the first diffraction pattern that Chemin produced. There's a sharp ring down here. That's actually from Kapton in the sample window, and we'll come back to that in a bit. So in 100 years, we've gone from von Laue's system here to the Chemin instrument on Mars. But really, there's a lot of heritage that's similar. You have an X-ray source, a sample holder, and a detector. In Chemin, we have an X-ray source, which actually integrates a power supply. That was a challenge. A sample holder that has a number of sample cups with windows on a rotating wheel, and then the detector. Here's our CCD. So in 100 years, we've come quite a ways, but it's kind of sobering to think that it took us 25% of that time to develop the Chemin instrument. This is a picture of one of the pairs of the sample cells, and you can see two different colors here. The yellow is a Kapton window. The white is Mylar. And why do we have two cells? The Kapton is extremely durable, and we have it there for insurance primarily. The issue with Kapton is it does have a small diffraction peak at low 2 theta that could conceivably interfere with some of our smectite identifications. And this image actually was showing a sample moving under piezoelectric vibration. And that's how we get our infinitely variable grain orientations, is by shaking the sample inside the cell. We'll be talking about two samples today. The first is the scoop, and the second is the drill sample that John just covered. These are the images of the two spots that were sampled at about the same scale. Here's our scoop sample at Rocknest, and then the John Klein mudstone. And John has already described the color differences here, so I won't go into that. And these two images that John showed summarize briefly what these images look like in a 2D diffraction pattern on the CCD. So these are the actual CCD images, colorized for intensity. And again, as John pointed out, we're getting a lot of dispersed but very low 2 theta diffraction here, and that's our smectite. It's something we came here to see, and we did see it. First, I'll go into a little detail on the Rocknest dune, then I'll skip over to the John Klein drill sample, which is very preliminary. This is what that 2D pattern looks like if you unravel it into a 1D diffraction pattern of intensity versus degrees 2 theta. And again, this is in cobalt, not copper, diffraction. The blue pattern is the basic pattern that comes from the instrument and deconvoluting that 2D array. I mentioned that the Kapton peak here has its own little signal. It's not very small, but a lot of sample, it'll be dwarfed. Most clay minerals would be out here, so it's not a direct overlap, but it can be an issue. So we took this sample and then loaded it into a Mylar cell so we could get rid of that. And so the pattern I show later will be in the Mylar cell. There we go. And this is a summary, and if you were paying close attention to John's talk, you'll see that we indeed do have a lot of basaltic minerals here. We have plagioclase, forsterite, augite, pigeonite in particular, indicating an extrusive type of mafic igneous rock. The magnetite in this sample, was only 2%. We do have anhydrite, but at a very small amount. I want to point out here that some of these minerals have identifications that helped us to improve the fit of the pattern, but the errors are close to the amount identified, so we're not confident that those are actually present. So be cautious about those units. From the diffraction pattern, though, we can also get unit cell parameters, and these are the cell parameters for our igneous minerals, feldspar, forsterite, augite, and pigeonite. And these can give us compositional information, which is very important because eventually we'll be comparing this with the APXS data and with some of the ChemCam results that are giving us chemical constraints on what this rock is actually like in terms of chemistry that we can then fold the mineralogy into. We also look at the amorphous component. This rise in background indicates that there's a fairly large amorphous contribution to this diffraction pattern. And this is the result of a full pat fit. And we did 3 different scoop samples, scoops 3, 4, and 5. We have, as an example, a Gusev type composition basaltic glass. This does not imply that we think that is actually what this amorphous component is, but it's a decent surrogate. And we also have, what I won't go into in just any detail with this talk, suggestion that we might have an allophane type component. But you can see, as John said, we've got roughly 30% of this amorphous component at Rocknest. Now, we talked about comparing that to the APXS results. And when we do that, you can tease out what the compositional constraints on this amorphous component, because we can use 2 approaches here. We can either use representative known compositions of these basaltic minerals or the ones that we actually define from our cell parameters. Both approaches lead us to the same place, that this amorphous material is fairly high in iron, sulfur, and titanium. It still has a lot of silicon. It also has almost no magnesium, which really surprised us. It's probably a complex mixture. We do not believe that this is a single amorphous phase, but it's a very important phase, as you'll see when you hear the presentation by Sam. So what does this actually look like? Do we have any terrestrial analogs that might give us a handle on what we're looking at? And it's really remarkably similar in many ways to basaltic soils that are found on flanks of peaks such as Mauna Kea. Not an entirely surprising result for Mars. So looking at a little more detail before we leave Rocknest, we evaluated lots of other minerals to try and fit this pattern. Most were rejected. We see no perchlorite phases. That doesn't mean they're not there. Our detection limits are fairly high. They're going to be about 2%. And you'll see a discussion of that with Sam. There were no phyllosilicates. That's critically important. No ferric sulfates, no Fe sulfates of any kind. No hydrated calcium sulfates. We just had the anhydrite. Our detection limits of 1 to 2% allow us to identify quite a number of phases here. It's a very rich and rather complicated sample. But again, going back to this amorphous phase, there are no hydrated phases that were crystalline, so that the water that is seen in analyses by instrument like SAM are in this amorphous material. And when you proportion that to the amount of amorphous material that's present, that's a lot of water. It's a fair amount of water. Now, just quickly transitioning to the John Klein mudstone. And this is going to be preliminary. We just got our last analyses of this sample before conjunction to bring us to about 20 hours of analysis, which is really our minimum to try and tease out especially minor phases and some of the details of the smectite. But there are some things that really stand out. The first is that the basaltic minerals very similar to what we saw at Rocknest. We're still working on the cell parameter refinements for those. We don't have those at this talk. That'll help us to constrain whether they are indeed very similar or just genetically, generally similar. But what really stands out, and the most critical thing is here, we do get this broad 001 diffraction of a smectite phase. There are clay minerals here. We also see basanite. We have a hydrated calcium sulfate, albeit there's probably not very much water in a basanite at Mars surface conditions. We expect this to be fairly dry. So when you think back to the image that John showed of these hydrated veins and blebs, I think there's a good chance we may eventually see gypsum here, which would be fascinating, and it really complicates the story because we have gypsum, basanite, and anhydrite. And again, this magnetite. The main contribution to magnetite is right here, and there's a whopping amount. But we also still have an amorphous component. If this were an extremely wet and reactive environment, I'd be surprised if that were still there. The crystalline component, if you look at this, and again, think back to John's talk, if you really got a good memory, you'll see these numbers aren't the same because we were still processing data. We're still looking closely at our results. But again, we see the same basaltic minerals, plagioclase, forsterite, 2 pyroxenes. A trace of sanidine seems a little more prominent here. Again, high magnetite. This is at least 2 and probably 3 times what we had at Rocknest. Very fascinating. The quartz is probably near its detection limit there. I have not put the errors up here because we're still scrubbing those. But again, anhydrite, basanite, and smectite. And the basanite and the smectite really stand out in this sample in comparison to what we saw at Rocknest. So just a quick comparison of the mineralogy of these 2 samples. There are lots of similarities. We have those common basaltic minerals. We have anhydrite in both samples. An amorphous component, it's still there in this mudstone, but it's far less abundant. Is it the same amorphous material? We have no idea right now. But by comparison, especially with the APXS data that's going to come back on those drill piles that John showed in one of his last slides, we'll be able to tease out constraints on what the composition, the chemical composition of that amorphous component is. And that'll really help to try and understand it. No hydrated Fe sulfates, no ferric sulfates, indications we did not have a very acidic environment. And the big differences are this presence of smectite, the presence of basanite, and this abundant magnetite. So last slide here, some inferences from what we've seen so far. Again, we have a basaltic source. Not surprising. This is what we anticipated. As John mentioned, though, a lot of these seem to be relatively unaltered. It's a little difficult to tell from the X-ray diffraction data. Some of the amorphous material that we see may not be a separable phase. Some of it could be alteration on top of some of these primary igneous phases, but our suspicion is that it's not, or at least not the most abundant component of that amorphous material. Smectite is really abundant. It's in this mudstone, but it's completely absent at Rocknest. And what's that telling us? One of the indications is that these sources of smectite were not so widespread and so heavily processed by aeolian material, by aeolian processes to deliver them to aeolian deposits immediately nearby, such as Rocknest. This may be a somewhat rare kind of environment that's just being exhumed and processed and delivered right in recent time. And again, absence of ferric sulfates. We've got the calcium sulfates, we have no ferric sulfates. It looks like a fairly benign environment, habitable environment in terms of pH. And the X-ray amorphous components are present in both. Again, we don't know if they're the same, we just know that they're there. Recrystallization by reactive solutions and high temperature appears not to have occurred in this sample. Again, a good sign if you're looking for biotic media, that you have not cooked and reacted your primary deposit to the point where none of this could be recognizable. So there is a chance there. We've not seen that yet, but there is a chance. Thank you.
Thank you, David. We can take time for one question. There is one from François Poulet, which is there.
Thank you. You have found the magnetite and concretions in the soil. So I wanted to ask: is this the composition of these concretions the same as hematite blueberries found by Spirit and Opportunity rovers back a few years ago?
We did look closely for hematite and did not detect it. That doesn't mean that it's not there again because of our detection limits of about 1% to 2%. The magnetite is actually interesting. I mentioned that I didn't show the cell parameters for these phases, but the cell size for the magnetite is smaller than we expected, a little bit smaller, and there are a couple of ways to do that. One is to go towards maghemite, so we might have a bit of a ferric component within the spinel phase, or you could also do that by putting chromium into the structure, which you do see in some Martian basalts. I'm not sure if we're going to be able to resolve that, but one of the targets that we might go to next would be a very concretion-rich zone. And if we see an increase in magnetite or we start seeing hematite, that might help us to sort out what those concretions actually are.
Okay, could you tell us a little bit more about the nature of the smectite?
The nature of the smectites. There are certain things that Chemin can't do. We do not go to the high enough in 2 theta to see O60, so we can't really pin down whether they're dioctahedral or trioctahedral. That said, I'm not the person to really describe this in detail. David Bish and Doug Ming have been looking at this pattern, and they're looking at the O2L bands. And if you quote me on this, I'll shoot you. But there is a chance that this is, it could be a trioctahedral smectite. And that's about as far as I could go right now. It's certainly not heavily hydrated. The centroid of that 001 peak is at about 10 degrees. So if the interlayer water is gone, which is what you'd expect in a Mars environment.
Thank you very much, Dave. So it's time to move on to the next speaker, Sylvestre Maurice, that will give an overview of the 100 sols of ChemCam operation at Gale Crater. Sylvestre?
Yeah, thanks a lot. Well, good afternoon, everyone. I'm giving this talk, of course, on behalf of a big team, the ChemCam team, as well as the MSL team and ChemCam team mostly between the US and France. ChemCam, since it's the first time we're talking about ChemCam in Europe, I thought I would give you some basics of how that technique works. ChemCam is based on laser-induced breakdown spectroscopy. That is a technique that is used in lab, is used in industry, but on very, I would say, prepared sample. Here we're using it not only on Mars, but on raw geological sample, and that's adding complexity, of course. That technique relies on a laser, so we have a pretty powerful laser. It's a pulse laser. We focus on a target up to 7 meters. We create a plasma at about 8,000 degrees, and we're reading the light from that plasma from the UV to near infrared to extract the chemical composition of the targets. That technique can go up to 7 meters. As you can see here, this is what we've been doing for the first 100 sols in terms of targets. People have asked us, usually targets from 2, which is more or less when we touch the ground, to 7 meters, but most of the targets are between 2 and 5, while we can shoot almost everywhere as long as we don't shoot on a rover. Okay. The spot size is very small. It's 0.5 millimeter maximum. And of course, it's very interesting to find a mineral, but sometimes you need to do averages to get the whole rock composition. To know or to find out where is that spot size exactly, we put on what we call the RMI. It's a micro imager that goes with the LIPS capability. It's a reflight. It's a spare from Rosetta. And that's giving us a very small field of view, but that size at 10 meters, but the high resolution to observe what the different targets we're shooting at. This is the kind of activities we have been doing on MSL for the first 100 soils. We call them first-time activities to learn how to use it. Sometimes we do single points, a point that we're shooting maybe 30 shots or 50 or 100 laser shots, and that's where you try to get a composition, measurement of the composition of your target. This is in soil. That explains why you see such a big hole. Well, it's not very big, but it looks big. All these images are being taken by our RMI. This is what we call a raster. It's a line of 5, 10, 20 time 30 shots, 50 shots. That's where you want to, for example, cross a cranial vein, just like a calcium sulfate. And this is a 2D raster that now you want to investigate also the spatial variation of the composition. We can do a 3x3, 5x5 when we want to match with what APXS is doing just to match their field of view. Sometimes we do depth profile, which is shooting at the same place. Here we're shooting 4 times 150 shots, 600 shots in the same spot. Try to go deeper. We can go to, on soil, it's easy to do a few millimeters. On rocks, we think we can do 0.5 millimeter, or it depends on how hard is the rock. Sometimes we can take RMI only, and because we have a spectrometer, what we can do is take passive spectroscopy, and that's very important, and it's promising some good results. Over the first 100 soils, we've shot something like 14,000 times. That's that many spectra. Each shot, we have a spectrum, okay? We have passive spectra, some images, and so many good and interesting data. By the way, this is a conjunction now. That's where we are at. So we keep ramping up our number of shots, and as of yesterday, we were about 44,000 shots, and that's many spectra. And for approximately 1,300 data points, single points with many shots each. Okay, that's where we are. This is what it looks like a ChemCam spectrum. It's being registered by 3 different spectrometers. That one's cover the UV from about 240 nanometer to 345, and then that's visible, and it goes to visible again, and to the near infrared to roughly 900. The LIPS technique producing a lot of lines. I mean, they're not bumps, they're real lines with a very high signal-to-noise ratio. We have about between 120 and 170 lines per spectrometer. And each line corresponds, of course, to an element. So far, it's extremely easy for us to see all the major elements. That's very easy on every single target. We can also see some minor untraced element of interest, like the lithium, of course, or strontium, barium. We can see the carbon, but be careful, the carbon comes from the coupling of the plasma with the atmosphere. And we can see the hydrogen. That's extremely important for us, and we're working a lot on this element. And I refer you to a couple of a talk by Suzanne Schroeder coming later this week. We have some elements that we were not sure that we could see easily. They're so important, sulfur, phosphorus, and chlorine, but they do show up when there's a few percent, and that was important for us to identify calcium sulfate, for example. This is just an example of a line, just like strontium, that varies by a factor. It's a 12 range over the data set. Well, the imaging capability, I refer you to a couple of posters by Yves Langevin and Stéphane Lemuelic. The main goal was to get the texture and the morphological context, and as well as detecting the laser spot. This is done by the drill hole, and you see the different spots. Here we could sample the rock itself, and then this is the tailings from the drill. That's very under investigation. Of course, it's extremely interesting. The resolution is about 50 microrad, and people have learned how to build mosaic and do Z-stack, and even we're borrowing colors from our MassCam frames. So that's a mix of MassCam and ChemCam. Okay, this is just to finish up on what ChemCam can do, a summary of, well, no, it's not a summary, it's a typical investigation we can do on a rock. This is rock nest 3, and over nearly 2 weeks, we put, I think, something like 2,000 shots on that rock. Of course, this is 1 by 10, this is 600 shots. That's diagonal. So depending on what we're looking for, sometimes we either go everywhere on different, just to find where we could guide the rover, help everyone else, or sometimes we take our full speed on only one target, just like we did. Look at this one, and I come back to that, how ChemCam can remove the dust. The spots are very tiny. You could see them. Well, I can see them. I'm not sure you can. They're 0.5 millimeter, but the dust is roughly 1 centimeter wide. So from there, where do we go? Well, you got a spectrum. You turn your spectrum into some data processing in a process spectrum. That's pretty easy. Well, normal work, I would say. Then turning that into some products. I think I wanted to put that to tell you what we have. Using our database of lines, NIST or Mars database, we can detect some elements and tell you if they are here or not, just like chlorine, for example, phosphorus and other. If we're using our onboard calibration targets, we can do relative and absolute abundances of, for example, minor elements. If we rely on a big laboratory database that we're still building on with our spare instrument, we can tell you using some statistical method. So we can do some trend and classification. And the one we're using is often ICA, just like PCR, and some clustering. Or if you're using PLS, we can absolute abundancy. So depending on the processing we do, we have different results, and they try, of course, to be complementary. Now, some of the results along the traverse, John has introduced that traverses with going from Bradbury landing site to the triple point and Glen Elg. What's happening here is very interesting. I'm still going to focus on that first place. It's in the Omoki region. And if you think it's one unique place, you will see there's so much diversity here. These are the different targets, and I think ChemCam has been heavily used, so we've been shooting on most of them. What we can do here along the traverse is to plot the composition. That one is being extracted from our PLS technique using our database. And you see that here we have a silicon as a function of the along the traverse. This is not the distance, it's only the different targets. That part here would be compressed here near Rocknest. There's a break here. There are obviously two different populations, and they break here between a place called Antona and Akaicho. If I look at the first part of that traverse here, you see some very silicon-rich targets that we've identified also with low calcium, a lot of variations. We think they're alkali feldspar. And if you look at the texture of that rock that John was showing earlier, the coarse grain, typically igneous rocks, and it's, I think, the first time we've seen them with a characteristic size of 302 centimeter for this coarse grain. We've seen the silicon-rich, there's alkali-rich, and I'll show that later. And we think that it makes sense with some recent discovery from orbits of feldspar-rich areas. And also, as you know, there's this NWA 7034 that is showing this kind of chemistry. Now, if I move to maybe still on the first part of the traverse to this part here, there's someone that doesn't belong like the other. It's called Link. And John has introduced that too. It's a conglomerate. You see that the pattern is very different from what was before and what was after. If you look at the texture, it's also different. It's a line tone pebble kind. It's very rich, enriched, not very rich, enriched in silicon as well as potassium and sodium. And we think we're looking at pebbles coming from the crater rim. Refer you to a poster by Nicolas Mangold, and looking at the cement that is titanium and chromium rich too. It shows some hydrogen, but so far we have not really resolved the origin of this hydrogen. There are many interesting things along this traverse. I could refer you to this point here that are extremely low in silicon, and to compensate that, the anion that is really missing, in that case, is a chlorine. And we also have a bit of phosphorus. Later on the mission, we would have same kind of pattern, but with calcium, with sulfur. That's our calcium sulfate John was talking about. If I go along the traverse on the second part from soil 50 to 90, you can see that it's enriched in iron. We've measured more than 25% iron oxide. And it is sedimentary in its aspects and structure. It could be volcanic in its origin. That's under investigation. Well, that figure is pretty nice to synthesize what we've seen so far. It's the sodium as a function of potassium, and it shows us 3 different units. That unit here corresponds to early on the mission. There's a mixing line here. The rockness part is the second part of the mission of the traverse, and the mixing line is very different, and dispersion is much smaller. And you have some what we call outliers. I show only 2 here: Link, the conglomerate, and Bathurst is different from anything else. Even if later on the mission we're filling more or less this gap here, this is still an end member, and I refer you to a talk by Violaine Sauter and a poster by Gilles Berger. After rocks, we can go to soil, and ChemCam can see soils with the RMI and, of course, sample the soils. Before the transition, I mentioned we had big coarse pebbles. It was more fine grains after the transition. And we've been studying in great details all this diversity. And we see kind of 2 end member when we plot the silicon here and the potassium and sodium here. We see something we call type 1, which is a mafic component that is seen from Bradbury all the way to 100 Sol. That is very global. They're very fine grain. When you look at the chemistry, it's very much like what we expect the soil to be on Mars from APXS, mostly on Mer. The second part is also very interesting. The second type is a felsic component, which is more local, and it's a more coarse grain. And we've seen it only on the first part, just up to Anton. There's a talk by Olivier Fourny and Pierre-Yves Mélin on Wednesday, Walter Gertz, and a poster too. So that's what we have on soil. And to finish up the dust, that's very qualitative. It's just been shown this morning in a press conference. It shows that dust is everywhere. We knew it. But with ChemCam, every time we're shooting at a target, the first shot is always dust. It's so easy, so predictable. Look at what an example here on a graphite target we have on board, where you were supposed to have only carbon and maybe oxygen because of the coupling with the atmosphere. Well, that's true for the shot 50, but the first shot is very different. It's magnesium, calcium, and so on, and even hydrogen, and it's obviously the dust. And the dust is everywhere, and even when we've shot inside of the drill hole that was done a few days before, we got dust. It never happened that we didn't get dust on the first, a dust fingerprint on the first shot. If I look at that plot here with the 2 end members of the soil, enriched in hydrogen as well as alkali for the coarse one. The dust is here, which is dust is always richer in hydrogen than most of our targets. 85% of our targets are poorer in hydrogen than what's been seen on the dust. We're still, of course, working on numbers in terms of turning these two qualitative into hard number for the hydrogen. So, as a conclusion, ChemCam is performing very well so far. The instrument has been highly used. The instrument can be used in many different kind of configuration. Of course, our chemical data don't make sense if we don't compare them with APXS in the first place. And that we have to be very careful because of the size of our interaction, of course, with Chemin, obviously, and SAM, as well as the imaging capability. So that's just a summary. We've seen the dust, diversity of soil, the feldspar-rich part, the conglomerates, the Fa-rich sedimentary rocks with calcium sulfate, and so on. And just to remind you that on PDS, you can now have access to the first 90 days of the entire data set. It's important. You're welcome to use them and ask us how to use them, of course. Later on, we present data on Yellowknife Bay just to tell you how good the rover people are now This is ChemCam. This is a drill hole. It's teeny. And that's how, you don't see it very well, but we shot 1, 2, 3, and that mark here is our laser. So we could do a first stratigraphy inside of the drill hole. Thank you.
Thank you, Sylvestre. We have time for one single question. Okay.
You measure elemental byproduct of the laser irradiation. Now, how much does it depend on how the elements are bound into minerals?
That's a very good question, Bernard. Two things. First of all, it's true that we don't see any molecular. We see some molecular bands sometimes, but we destroy everything. 8,000 degrees, you're burning everything, so you get only the elements. But even so, the elements depend slightly, the response depends slightly on the matrix, what we call the matrix effects.
Oh, yeah, sure.
That's why we're using this statistical tool to extract that information. It's not as simple as taking the height of a peak and turn that into a composition. You have to take several peaks, look at the pattern as well as the height to get the information. So we have a way to go around that, but absolutely true, the matrix effects are important.
And now, if you have a laser shot, you induce also chemistry between the different minerals that are mixed.
Well, that's another point. It's related to the size of our interactions. And usually we think that with that small size of a laser we could eat different mineral phases, but which way do you want to go? Do you want to see one phase and you get one mineral, or do you say a mix and you get a better understanding of your rocks? I can go both.
So we need to move on. Sylvestre is around during 3 days, so you can ask him questions after the session. We move to the next talk, which is by Paul Mahaffey and the SAM investigation at Gale Crater, and the talk is presented by my co-chair, Patrice Cole.
Okay, thank you, Nicolas. So this is my pleasure to present the early results from the Curiosity rover's investigation by SAM, sample analysis at Mars. I will especially focus on rock analysis, because Sushila Troya will give the next talk, mainly focusing on atmosphere. So I'm giving this talk, of course, on behalf of several co-authors, a member of the Mars Science Laboratory Science team, but I want especially to emphasize Paul Mahaffey, our PI, that was unable to give this talk due to some NASA trip restriction. And then I'm giving the talk on his behalf. Then, as you know, of course, one of the main objectives of MSL is to assess the habitability of Mars, and SAM is really one experiment devoted to support this investigation. For those who are not aware of the Curiosity payload, SAM is located in the body of the rover. It's an important instrument in terms of size, and it's sharing what we call the analytical laboratory with Chemin, that Dave was just talking about a few minutes ago. So, some illustration of the SAM suite, first to show that it's real, and to remind you that it is a combination of 3 instruments. One is a quadruple mass spectrometer developed by the Goddard Space Flight Center. One is a gas chromatograph developed by the University of Paris and run by CNES, the French Space Agency. And the third one is a tunable laser spectrometer developed by the Jet Propulsion Laboratory. Here is a global view of the whole set. Of course, we have several subsystems, including subsystems to process the gas, to manipulate the solid sample, and also some pumping device, especially because the fluid circulation in the analytical system is a key parameter for us. So, just to be frank, this is a very simplified scheme of SAM. So it's somewhere there to show you that it is complex, but also to show you that we are really in front of an instrument that has analytical huge capabilities in analytical chemistry, because I will describe this later on. And we have the capability, like in the lab, to try to make some sample talk, changing the measurement mode we use, because we can sample atmosphere. We can also recover some solid sample. And depending on the pathway we will use, we can combine. We can have direct analysis by quadruple mass spectrometer, or a dedicated coupling of the gas chromatograph system that separate the component of a mixture and then a QMS, or some combination of the QMS and TLS. So a lot of choice that the team has to take into account. And just to convince you that it was a simplified scheme, I just add the more complex scheme with a lot of heaters, valve, pressure sensor, because I think this is probably at the surface of a planetary object, the most complex instrument that man put there. So it is quite a good challenge. So talking a little bit about analysis and then results. So here you have the main mode, measurement mode, that we have for SAM. I will not talk about the one on the right, because they are devoted to the atmospheric measurements, so it's the job of Sushil just after me. So I will focus on the left part, more devoted to the rock volatile measurements. So as you can see, we have some modes that are based on analysis doing combustion of the sample, also analysis using wet chemistry, especially devoted to try to issue some refractory organics from the sample. But for the moment, since the start of the investigation by curiosity, we only use the first mode, that is EGA for evolved gas analysis, which principle is quite simple. You put your solid sample in kind of an oven, you heat under an helium flow to 800, 900 Celsius, as a function of time. You have the QMS that in live try to assess the identification of the volatile that exists from the sample. And you can have specific option where you can transfer part of the sample later on to the TLS or to the GC for GCMS analysis. I will come back to this later on. So apparently everybody wants to show the road of the rover since the landing at Bradbury Landing. So I made the same. And during this traversée, you see that we made several stops for analysis, but one stop was clearly longer than the other one at Rocknest. This is a view, most very famous pictures in high resolution of the rover at Rocknest. So Rocknest is this kind of aeolian bed form, anyway, aeolian origin material. And in front of the rover, you see several trenches, and in the very front, a wheel scuff that was made to check that the dune is really like it appears, I mean made of soft material. Then we are able to make some scooping, and with a subsystem of curiosity called Kimra, we sieve some specific range in terms of particle size, less than 150 micrometers, and we carried out several analyses by SAM, you see, during approximately 10 to 12 days. Then before using SAM, having a look to the rough composition of these finds with APXS, another instrument of the payload, we see, with not a real surprise, but it's good to have a clear view, that the main composition is similar to what was observed by former missions like Spirit, Opportunity, for some reason explained especially by Sylvestre just before. And then it was time to process this Scoops sample with SAM. So the idea is to deliver the sample, part of the sample, to the SAM sample manipulation system. You have here a top view of this system. It's a lot like in the order of 80 tiny metallic ovens, in which, so you can fill one with this sample. Then the oven is heated to approximately 830 degrees. I'm more talking about the sample temperature. Anyway, some hundred of degrees, 8 to 900. And we follow what is evolving from this heating by mass spectrometry using the QMS. As you can notice, there is a pathway there where we can store, after analysis, we can trap some material for analyze it later on by TLS, so the tunable laser spectrometer, or if we prefer, by gas chromatography, again to separate the constituent of the mixture. Then we have in mind to search especially for traces and to try to analyze them using mass spectrometry. First, I will describe some results looking to the most abundant volatiles observed in the rockness sample. So there are 4. In order of abundance, we have H2O, then CO2, then O2, and then SO2. As it was shown also before, most of the evolved gases are primarily from the amorphous phase revealed by Chemin, and this includes especially the few % of water vapor that we observe there. If we go to the volatile number 2 in terms of abundance, CO2, we saw that we can see that the signature is much more complex and appears to have several contributions to explain the global shape of the release of CO2. So probably these different modes are related to different origin. So we are pretty sure that the high temperature component could be from carbonate, magnesium carbonate or iron carbonate. And especially for the mode observed at lower temperatures, the investigation is still under process, but we have a good option, especially I try to convince you that the size, the volume of SAM is pretty huge, and that it's hard to have, we'll say, a threshold, an instrument completely empty of anything, and probably some material we have inside the system, for example, MTBST phase, that is this huge hydrocarbons molecules with some fluor and silicium atom, may explain this kind of CO2 formation, because when you have these compounds plus heating, you can generate, and water, you can generate chemistry, and then this chemistry could lead to oxidation, combustion, and at the end, CO2, like in Earth's atmosphere or Mars atmosphere. All right, going to the dioxygen and sulfur compounds. So the evolved oxygen may be from the decomposition of a perchlorate, such as CaClO4 2 times perchlorate. And concerning the higher temperature sulfur-containing compounds, this indicates the presence, as already described also, of sulfate or sulfide. We are also under investigation to analyze some trace level signals, for example, searching for nitric oxide or hydrogen cyanide that maybe are present in the signal, but with, we'll say, not a lot of warranty for the moment. This is under investigation, characterization, I will say. So now I'm moving to the part of the sample that was analyzed by GCMS, so a mode devoted specially to try to find the compounds that are really at the trace level. And looking at organics in general, we mainly find some chlorinated compounds, some that are well-known, we'll say, in terms of Mars investigation, like chloromethane or dichloromethane, because they were observed by Viking GCMS on 2 sites. Anyway, what I want everybody to keep in mind concerning the rockness analysis is that at first level, SAM shows that there is not abundant organics in this soil. This could be, of course, explained by the fact that this kind of material evolve very quickly under UV oxidation processes like hydrogen peroxide or other oxidants. So it's not a real surprise. After we have, it's true, some traces of these chlorohydrocarbons. And for the moment, we can explain that the chlorine is, of course, coming from the thermal degradation of the perchlorate I was mentioning just before. So the perchlorate is the source of chlorine. And concerning the source of hydrocarbons, the other part of the molecule we have to explain, it could be from terrestrial origin or Martian origin. In fact, for the moment, we cannot really say, but of course, we have in mind that some carbon from molecule may be present in some system or in the sampling chain or whatever, could generate this amount of chlorohydrocarbons at trace level. Anyway, this is not a surprise to not find a lot of organics in such sample. And the curiosity search for organics in other environments and sample will continue, but where? For the moment, we are in Yellowknife Bay, so other speakers talk about these veins, or we have also nice environment showing dynamic transport. Anyway, early February, man for the first time make a hole at the surface of a planetary object. And Paul asked me to show you this first slide showing the result of this sample called John Klein, where once again we have the four main volatiles observed that are respectively water, carbon dioxide, oxygen, and different forms of sulfur, with some variation, because if you look more properly, you have, comparing to previous case of rockness where you have a decrease at high temperature of water, if you have another signature, maybe linked not to bonded water, but from structural water, maybe hydroxy groups. And in terms of organics at trace level, we are looking and finding, we'll say, very few organics, mainly chloromethane and dichloromethane, once again, anyway. For the moment, even if we are still under investigation at Yellowknife Bay, or if organics are present, they are once again at trace level, and the organic quest is still going on. So, during the conjunction, Paul takes time to give the program for the whole team. So first, he asked us to rest during the conjunction, or try to. Then he finished the exploration. Then we will have to finish the exploration of Yellowknife site. We have especially some decisional data to give to the whole team in terms of the organic content of the sample. And then we hope to begin our long journey to Mount Sharp, where we hope to sample ancient clays, sulfate, and so on. So as a conclusion, the SAM investigation at Mars report will continue very shortly with Sushila Treya. And I wish you, behalf of conveners, a nice Curiosity on Mars session this afternoon, but also next Wednesday. Thank you.
Thank you. Actually, we ran out of time, so I propose we just move on to the next talk, which is exactly the following of what we learned from Patrice. Next talk by Chris Wester and others, and given by Sushila Treya about the atmospheric composition from the SAM instrument.
Good afternoon. So, as you gathered from Patrice's call, that our leaders of SAM are not here, they've been grounded. Chris Webster was going to give this talk, and he's the lead for the tunable laser spectrometer part of SAM suite. And Paul Mahaffey, the PI of SAM, both of these people work for NASA, and they've been sequestered. This slide gives you a sense of the size of the SAM suite. And here is the instrument that was being integrated into Curiosity just before launch. This is the size, essentially, of a large microwave oven. It costs a little more pennies than the microwave oven. And it weighs approximately 40 kilograms. The instrument that Chris is holding here is just about the size that you see here, about half a meter or so, or slightly less than that. And it weighs approximately 3.5 kilograms. The SAM suite here, as Patrice just described, contains 3 instruments and a whole bunch of subsystems: the quadrupole mass spectrometer instrument, the tunable laser spectrometer, and the gas chromatograph. As Patrice pointed out, I'll be talking about the right side of this slide, all the cool stuff Patrice already described to you. I'm going to talk about the gases in the atmosphere, primarily the isotopes in the atmosphere. And we do these measurements in different modes. We can do the direct atmospheric analysis, in which we take in the sample, Martian air sample, into the mass spectrometer and measure the composition, including the isotopes. We can send gas also to the TLS, and the TLS has 2 channels. One of them is devoted to methane, and the other one to carbon dioxide. So when we send the gas to the TLS, at that time we are making either the measurement of methane or we are making the measurement of the carbon dioxide isotopes and also the water isotopes that I'm going to talk about. SAM has a bunch of other tricks in its pocket. We can do enrichment in the atmosphere. There are certain gases which are, of course, minor constituents of the atmosphere. In order to make their measurements, we need to do enrichment experiments. In other words, we remove the large gases like carbon dioxide, and we remove reactive gases, water vapor, carbon dioxide. We also can do gathering, and we do trapping. And all these processes can enrich the abundances effectively, the abundances of the minor constituents. And that allows us to make the measurements of things like methane with the TLS. We can measure the noble gases like xenon, krypton. Is that good? Yeah. And we can measure noble gases like xenon, krypton, and also the isotopes of argon, the primordial argon. The argon that comes from the decay of potassium-40, that's argon-40, and that's large, relatively speaking, is large as about 1%, and that we're able to measure in the direct atmospheric sampling. Let's first talk about methane. Everybody loves methane on Mars, and this is the update of methane results. Previously, we had reported methane abundance, which was just an upper limit, actually, and it still is an upper limit. And the upper limit previously was 3.5 to 5 parts per billion. That's what we reported. We've done a lot more analysis of the same data, and the upper limit now is 2.7 parts per billion with a 95% confidence level. The measurement is done with the tunable laser spectrometer, which is essentially a gas absorption cell, if you would. And the part here is the 4 optics in which we actually carry some methane from the Earth. And that allows us to know exactly where the methane lines are. So this is the region that we are working with. And this is about half a wave number region that we are really looking at. 3057.6 to 3057.8 wave numbers. And in this region are the 3, if you would, the rotational vibration lines of methane, and this region is the isotopes of methane. So in one pass of the laser, we know where these lines are, and then we pass the gas, the Martian air, into the Harriot cell, the gas absorption cell, if you would, do the lasing here. There are 81 passes with the effective path length of about 17 meters. And the measurement is done first with the cell empty. That allows us to make the measurement of the background. Then we do the measurement with the gas from the Mars atmosphere filled into the cell. And then we make the measurements again with the cell empty. So we pump out the gas of the Mars atmosphere from the Harriet cell. So we have background measurements on either side of the full cell. We know exactly what the background is. This is the result where you see the full cell result is over 3 sols with squares and circles and triangles. And the bottom part is the empty cell. It's essentially 0. And we take the difference between the two, and that gives us a value of 0.4 plus minus 1.1 part per billion by volume. And there's, of course, no definitive detection of methane. And the statistical analysis gives us 2.7 parts per billion as the upper limit with a 95% confidence level. The experiment will be conducted with the enrichment of methane that I talked about before. And when we do that, we can increase the sensitivity by a factor of 10 to 50, which will give us even a tenth of a part per billion, or maybe even less than that detection limit of methane. So, of course, we cannot report any isotopes because we haven't, of carbon and methane, because we haven't even detected methane so far, but we are monitoring it. Now, that small amount of methane, if it is there, could be produced from any one of the processes, the water-rock reactions, the UV degradation of surface organics, or methane-producing microbes on Mars. So as we monitor methane on Mars and keep making these measurements, when we have set even lower limits to methane, we'll still not be able to tell if the amount stays at about what we're seeing now, what the source of methane is. Now, let's move on to things that we can measure. I'm hearing a lot of echo here. Are you? Okay, I was going to stay away from it. The measurement of carbon dioxide isotopes were also made with the tunable laser spectrometer, as well as the mass spectrometer for carbon that I'm going to talk about in a moment. The region that we are after is this 3590.2 wave number to 3589.8 wave number, approximately. And again, a very small region of the spectrum where we can make these measurements. There are a whole bunch of these lines where we can look for the isotopes. This is a Hydrogen database from which these spectra are given. We can move about 3 wave numbers away from here, and there are prominent lines of water vapor that we can measure. So this is a good region for making the measurements of the carbon dioxide isotopes. And the second scan region, we can measure both the carbon dioxide isotopes as well as the water isotopes. Initially, when we proposed the instrument, we had 6 channels, but when push came to shove, we were left with 2 channels, and we thought we would never get water vapor out of this. But this is really lucky that we can move 3 wave numbers away, and we can get both the carbon dioxide isotopes as well as the water isotopes in this measurement. This is a result from a number of different sols over which the measurements were carried out, and you're seeing here the result for the oxygen isotope, the delta 18O, which comes out to be 4,800 per mil, and 48 per mil, and delta 13C, which is 46 per mil. And these measurements were carried out over a number of different sols. Now, both of these are telling us that the carbon dioxide is isotopically heavy in oxygen and carbon. The carbon measurement, the carbon isotope measurement, was also done with the mass spectrometer, and that gave us 45 per mil. So there is a very nice confirmation of the TLS result of 46 per mil in carbon delta 13C, and the TLS and the QMS agree very well, independent measurement. And it's also very different from what Phoenix measured. Phoenix measured isotopically light carbon dioxide and carbon, and we are finding that that's absolutely not the case. In water, so when we take some air sample into the TLS, as I said, we can move 3 wave numbers away from where we observe the carbon dioxide isotopes, and we can actually measure the hydrogen isotopes in water vapor. And that's what you're seeing here. This is the result for water vapor measured with TLS and SAM in the atmosphere. And this is a ground-based measurement that was carried out over a number of sols. And it shows that at the time of the measurements that the SAM measurements were done, there's a pretty good agreement. I also show here by way of comparison what we're seeing in the Rocknest aeolian deposit. And it shows that the Rocknest aeolian deposit we're seeing the absorbed water from the atmosphere. Essentially, the D2H values are very similar. So water is, the hydrogen isotope here is clearly showing that water is also isotopically heavy, just like the carbon and oxygen we saw in carbon dioxide. Now, this is a new result that we got just in the last week, and this is the result of the enrichment that we did in the mass spectrometer. And this is a result of the argon 36 to 38 ratio. And this analysis that I'm showing you here was within 5 minutes of getting the data. So the numbers you're seeing here, don't take them as the final numbers. We have done a lot more analysis in the last week. And this number has nudged up by about 5%. So the new number is about 5% higher than what it is. And I'll give you the number in the next slide. But this is a beautiful experiment where we scrubbed out the carbon dioxide and water vapor reactive gases. And we were able to, in effect, concentrate the small amount of primordial argon there is in the atmosphere. Primordial argon is on the order of about 5 parts per million. And so in order to make those measurements, we had to do the concentration by scrubbing out the reactive gases and things like that. You can see here the argon 38 isotope, and this is the argon 36 isotope. This is the ratio, rock solid. Very nice result. So what does that mean? So here we have the SAM result, and then I have a bunch of comparisons with Viking, with SNCC meteorites, with primordial argon. The SAM result is actually really good, really nailed this baby. Here, the error bars are so small that I cannot even show you the error bars. It's a very nice result. This is the result from Viking, and the SAM result is kind of at the lower end of the range of Viking values. The Viking result is such that it could be anywhere from the SNCC meteorite result to higher than the solar value, which is shown here, or primordial value, which is showing in the Sun and Jupiter. So the SAM result has resolved the discrepancy between the Viking and the SNCC results. The upper end of the meteorite value here that you're seeing is from EGU2013 meteorite, and that's a good example of the meteorite that trapped the recent atmosphere in its glassy fines, and that's what SAM measured here, and the meteorite value is very similar. Now, what does it tell us when we compare it to the solar values? The solar value is about 5.5. The Jupiter value is also about the same within the range of uncertainty. That's what we would expect. So when Mars was forming, it actually trapped the planetesimals that formed Mars, brought in this kind of argon. But over time, the ratio has gone way down. That's because of escape, of course. The lighter isotope escapes more easily than the heavier isotope. So over time, the heavier isotope builds up. So argon is isotopically heavy, just like what we found in oxygen and carbon or carbon dioxide, and also water. So my final slide gives you the values of all these things that I talked about. So argon is coming out to be 36 argon to 38 argon ratio is coming out to be 4.19 plus or minus 0.035. The numbers are going to change somewhat, but this is an analysis in the last week. The delta D from water vapor in the atmosphere is about 5,000 per mil, and the error bars are large because the amount of gas that we took in this experiment was rather small. Next time we do the experiment, we'll take in a lot more gas, and we can improve on the uncertainty here. The delta 13C is 46 per mil, and delta 18O is 48 per mil. So everything is isotopically heavy. Carbon dioxide is isotopically heavy, same as water. We had known about water before, and so is argon. And it's telling us that Mars has lost much of its original atmosphere in geologic time. So what comes next? Well, we will compare the values that we see in the atmosphere, the isotope values. This paper is only about isotopes. On Wednesday, I'm going to talk about the composition a lot more. That we'll compare these values in the atmosphere with the gases, the isotopes in the gases that are evolved from diverse solid samples. And so we've already done Rocknest, the Aeolian deposit of Rocknest. We've already done a good part of John Klein. We're going to be doing another one that John Gossinger just talked about. After the conjunction, we'll do that. We'll also enrich the krypton and xenon. We actually did make a measurement of nitrogen isotope. We are analyzing those data, but we'll do it again. And so the enrichment experiment is going to continue also, of course, for methane, and we'll be carrying out these observation measurements in the next several months. Thank you.
One quick question before we move on.
How much what? How much is lost?
How much of the original atmosphere is at to a level where it had significant change in the greenhouse warming of the Mars?
Yeah, I see what you're asking. Good question. Yeah, so Mars has lost nearly 95% of its atmosphere. That's what these isotopes are telling us. And so, Mars was most likely had much thicker atmosphere and would in turn mean that there was a good possibility of warmer and wetter. And we have other geological data which points in the same direction as John talked about. So indeed, in the past, the conditions were appropriate for habitable Mars. I guess that's what you're getting at.
So we move to our last talk of this session by Javier Martin Torres and a bunch of people from the REMS team and the MSL team, and this will be a review of the REMS instrument first results.
Okay.
Password.
Okay, hope that you're not very tired at this point. So I will try to be quick. I'm going to give an overview of the first measurements of the REMS instrument on the Mars Science Laboratory. I want to acknowledge here all my colleagues of the REMS team that are for different institutions in Spain, Finland, and the US, and of course to the MSL science team. Okay. Well, for those people that are not familiar with the MSL project, I would say that REMS is not an instrument that is in a single location. It's distributed in the rover. As you see here, there is two booms in the mast of the rover with the wind sensor. Well, boom 2, what we call boom 2, has a wind sensor, humidity sensor, and an air temperature sensor. Boom 1 is not visible here, but it's 120 degrees from boom 2. It has an air temperature sensor and a wind sensor too. And we have the UV sensor on the rover deck and the pressure sensor inlet. Well, you see here in more details the booms, boom 1, boom 2. You have the ground temperature sensor here, the humidity sensor here. This is the ultraviolet sensor with 6 photodiodes that measure the UV radiation from 200 to 400 nanometers. And well, REMS is a meteorological station that also measures UV radiation, so it's measuring pressure, air temperature, ground temperature, UV radiation, relative humidity, and winds. We are measuring at every second simultaneously. I mean, all these values are taken simultaneously at 1 second. And nominally, we had 5-minute measurements per hour, but this measurement has been extended, so we measure around 5 hours per sol. And at Sol 100, we had more than 2 million measurements. And well, what I'm going to present here is the science that we've been doing during these months with REMS. But first, I would like to explain a little bit how challenging it is to analyze data from REMS. Well, this is this would be the local environment, a typical local environment of REMS that everybody knows, the Gale crater. Well, we see that we have many problems. Well, the main one is that we are in a rover. So being in a rover is being in a big monster with it's a mechanical thing with a own thermal inertia. It has and not only that, the rover is heated by the RTG, which is at this point the hottest object in Mars right now. So we are close. I mean, the meteorological station REMS is located in the hottest point in Mars. So, well, we have also problems derived to, well, it's very nice for geologists to have these very different textures, very different kind of surfaces. But this is a problem when you try to measure the temperature of the ground, because every different kind of soil has a different kind of inertia. So this is another problem that we have to solve. The field of view of the ground temperature sensor is also a problem, because it's not always pointing the same kind of soil. And well, even the operations, the daily operations of MSL are a problem for REMS. Well, for example, the mast is many times shadowing the UV sensor, and it's not even shadowing at the same time all the sensors, all the photodiodes. So these are things that we have to take into account. And well, not only that, the rover is moving. So when the rover moves, the direction of the wind changes, the tilt of the rover changes, the field of view of the UV sensor changes, the thermal inertia, as I said before, changes. And I'm sorry. And as John was showing before, this picture, but with a better resolution than I'm showing here. Here we see ground temperature measurements, the minimum and maximum temperature. And as you see, as we cross different areas in the rover traverse, we have the differences between the minimum and maximum temperatures over the day are changing depending on the thermal inertia. So, well, how do you monitor the environment with a station mounted on the hottest spot in Mars, a huge mechanical obstacle, a 2-meter-long deck with a radiator on the back, a mast with a big head fully equipped with electronics that are partly absorbing the solar radiation and are partly shadowing and are thermally coupled with the detectors, and a structure that changes, tilt, orientation, the ground basement is changing every sol. The location with, I mean, we have moving objects around that are heated by the sun, that have their own thermal inertia. We have hot plumes from the radiator that are contaminating measurements. And we have this big metallic object on the deck with the film boundary layer is broken only when the wind is blowing in certain directions. Here we have a simulation of the plumes that are contaminating the booms of REMS. Yeah, this is contamination just coming from the rover. So, well, how we deal with that? Handle the data with care, isn't it? So this is what we do. And I wanted to show this because I wanted to show how difficult it is really operate in a methodological in a rover. And this is a problem that we will face in the future with future rovers. And I think that it's very nice that all the lessons that we are learning with studying and analyzing the data from REMS. And I think that we have done a lot of progress during these months. But well, not everything are bad news. Actually, we are the cleanest spot in Mars. We have, because the UV sensor, the photodiodes, the lifetime of the photodiodes is very much dependent on the dust. They are protected with some magnets around the photodiodes that try to lift out the dust that should deposit on the UV sensor. So I think we can say that this, you see here very nice the magnetic field and where the dust is deposited. And I think we can say that these spots here and inside the UV detectors are right now the cleanest spots in Mars. This is a good thing. And thanks to that, we've been able to do the first ultraviolet measurements from the Martian surface. This is a poster that we are presenting on Wednesday in the poster session, red posters from 5:30 to 7. And we are presenting the measurements. What are the problems that we face to interpret the UV measurements. But we are also showing very interesting results. That, for example, how the dust load of the atmosphere affects the UV radiation. Also, something that we can say that I would like to point out is that because we have been measuring in clear sky conditions at the beginning of the mission, the distance between the Earth and Mars was between the Sun and Mars was minimum, and because we are close to the equator, we can provide the upper limit to the incident UV irradiance on Mars surface. This is around 20 watts per square meter. I think these measurements are very interesting, and especially I will go deeper on this effect of the dust in the atmosphere on the UV radiation that is measured by the UV sensors. Because we are near to the equator, we are lucky enough to have at least 3 measurements per sol within the field of view for all seasons during the operations. This is another poster where we've been doing that we are presenting on Wednesday too, and this is showing the effects of Phobos and Deimos eclipses and on the Mars UV radiation. We were lucky that at the beginning of the mission in Source 37 and Source 42, we had two transits of Phobos first and Deimos after that, and on 42. And also there was something nice, is that, well, of course, we saw the decrease, we detected the eclipses in the UV, we saw the decrease of the radiation in the transit of the satellites over the sun. But interestingly, the first solar eclipse, the Phobos one, was an eclipse just of the diffuse light measured by the UV sensor, because we were lucky enough to be under the shadow of the mast when the solar eclipse happened. So this gives us an estimate of how much the UV diffuse radiation changed with the pass of Phobos in front of the sun. That was a 5% decrease. And we estimate that this is it was a linear thing when we related with the amount of sun that was covered. There was something linear, so we thought that this is because at that time we were in clear conditions, because we were just seeing diffuse light. And the Deimos eclipse was under direct light conditions. Deimos is smaller, and then the decrease of the radiation was also smaller at 2%. I'm not going to talk very much about pressure measurements, because there is going to be a dedicated talk on Wednesday by Bob Haverly with the preliminary interpretation of the pressure measurements. But I wanted at least to show these values from Sol 9 to Sol 100. And the blue, these are pressure in pascals, and the blue dots are instantaneous measurements. The red crosses are daily averages. And we see there's a large diurnal variation, as we were expecting, and there is an upward trend with season, as we were expecting also for the time of the year that we are. And we think that it is the polar cap is sublimating, and the pressure is increasing. So another interesting application of the UV sensor is that we were able to observe several obscurations that we think are due to dust devil. One that was very, very close to the rover because it had an influence on the direct light, and another one that was not so close to the rover and it had an impact on the diffuse light. These are two candidates, and well, this is a poster that we are presenting also on Wednesday, so I'm not going to spend more on that. Something very interesting is that because the RTG is heating so much, when the rover is moving and then stops in one place, it overheats the ground, and then the measurements of the ground are much higher when the rover stops there for a long time, or for 1 day or 2 days. And then when the rover moves again, the ground temperature decreases again. With that, depending on how quick the ground increase the temperature when the rover stops, is proportional to or is very much depending on the caloric capacity of the soil and the thermal inertia of the soil. So we are able to compute thermal inertias based on this on the slope of this change in temperature when the rover stops in one place. This is another poster we are presenting on Wednesday too. And now I would like to present what I think are very interesting data, and are data that combine information from several sensors. In this case, we are combining information from the UV sensor, in this case the ABC, which is the higher, the one that is covering a wider wave range between 220 and 380 nanometers. We are combining here the information from the UV sensor and ChemCam. We have that the UV sensor is measuring the irradiance on the ground or in the surface of Mars, and when we relate that, and when we compute the ratio between the top of the atmosphere irradiance and the irradiance measured by the UV sensor, we obtain the opacity of the atmosphere. So we have computed here, the red lines are the opacity of the atmosphere in the UV, and we are comparing here this opacity with the opacity in the visible measured by ChemCam. These are data provided by Mark Lemon. We see that they both share the same features qualitatively, that there is two regimes before and after Sol 90. This is for clear sky condition. We think this is for dust conditions. We are able to even to compute with these values the Armstrong exponent that give us the relation between the particles, how large are the particles, and we find that smaller particles are in this in the clear sky conditions, and the bigger particles are after the low particles in the atmosphere. This is a very interesting result. Another interesting one is a combination of the UV sensor and the ATS. We have that the UV sensor. Here we have again the opacity of that I showed before, and when we compare that with the diurnal thermal range, that means the difference between the minimum and maximum air temperature during the day, we see that this difference correlates very well with the UV opacities. This is a very interesting result, because up to now, it has always been thought that the air temperature is very much dominated by the surface, and here we are showing that it's very much dominated by the dust in the atmosphere, by the aerosols in the atmosphere. Well, just quickly, can I go to this one? two slides. Well, this is we can measure separately the global and the diffuse UV radiation, and when we saw that these are the UV global radiation from all channels, we see that they share the same features. And very interesting, we see that after Sol 90 side, where there is the dust of the load in the atmosphere, there is a strong transition to lower irradiances, also the higher opacities. In this figure, we see that when we compare the UV diffuse light at 6 p.m. local Martian time and at 7 a.m., we have that the fused light is not symmetric, it's asymmetric. That is telling us that maybe there is aerosol dynamics in the atmosphere. And when we correlate the UV with the maximum temperature of the ground, we see that the maximum temperature of the ground are very much affected by the opacity of the atmosphere. This is another interesting result for Mars. Well, here is showing the opacity with the average of the ground temperature, and we see that there is a correlation too. I wanted to tell you that there are other REMS team presentation at the EGU on Wednesday, 2 talks by Bob Havel, Vicky Hamilton, and then several posters in the afternoon. And well, I just would like to summarize with this slide. We have learned a lot how to deal with the local factors affecting REMS measurements. The measurements look very repeatable from sol to sol, and we see that the pressure increases with time. Most blips in the data seem to repeat from sol to sol. Right now, pressure, UV, and ground temperature sensors are providing very valuable information. And here we see, well, these are the number of conclusions from every one of the sensors, the UV, the pressure, GTS. And what we are doing now is combine information from different REM sensors and other MSL instruments to characterize Gale environmental conditions and atmospheric particle size, surface atmosphere interaction, particle size, and all that. Well, and very interesting science is ahead of us. Thank you very much for listening.
Thank you, Javier. So unfortunately, we won't take any question, but Javier will stay there because there is a session within 12 minutes from now. So just to remind you that the session is not over, we'll continue this session this Wednesday. Rendezvous at 10:30 in this room, first for oral session, the morning, the afternoon, and then a poster session. Thank you again for attendance, speakers, and so on. Thank you.